Iain Beaton is going to be talking about almost all domination polynomials are unimodal. So yeah, thank you, Iain, if you'd like to begin.
Thanks, Carrie. So as Carrie said, my name is Iain Beaton. I'm going to talk about the unimodality of domination polynomials, and this is joint work with my supervisor, Jason Brown, at Dalhousie University in Nova Scotia, Canada. So I'm going to start off with a few definitions. I guess not everyone here has a full understanding of graph theory, but given the time constraints, I'm just going to jump right in and go to a dominating set. So a dominating set is just a subset of the vertices here, such that every vertex not in our subset has a neighbor in that subset. So if we consider a graph here on 7 vertices, if we color 4 of them black, this is a dominating set because all of the white vertices or the non-dark vertices are adjacent to or next to something in our set. So this would be a dominating set. For any graph, there's multiple different dominating sets. So this is one of order 4, this is one of order 3, and here's one of order 2. So what we're going to be talking about is the domination polynomial, which basically takes all those dominating sets in a graph and creates a polynomial, a generating polynomial. And the coefficient of kind of x to the I in our polynomial is just going to be the number of dominating sets of order I. And we denote that with di. So that's going to be pretty important here. So this talk is on unimodality of these polynomials. So what does that mean? Basically, if you're to think about it as what kind of a distribution, so if you're to line up these coefficients, we call a polynomial unimodal if those coefficients kind of have one peak. So if we start at d0 all the way to dn, there's going to be some point in between dk where it kind of increases up to that point and then decreases down after that point. And this is kind of something you would see in statistics or kind of that defined in that area. A stronger condition is called long concavity, which is rather than looking at the entire sequence, if we just look at kind of 3 consecutive coefficients, if the coefficient di squared is at least the product of the 2 coefficients on either side of it, we call that polynomial log concave. And this is not so important to what we did, but typically when you look at unimodality, you look at log concavity because log concavity actually implies unimodality, and it's sometimes easier to prove. So that's usually how these things get proven for polynomials in general, but we're actually just going to be looking at unimodality. So for an example here, we have a complete graph on m vertices. This is just an example on 8 vertices, but the domination polynomial of the complete graph, well, if we think about taking any one of these vertices, that's going to be adjacent to everything else in our graph. So the number of dominating sets of size I is just going to be every possible subset of size I, meaning that our coefficients are going to be our binomial coefficients, and by the binomial theorem, the domination polynomial of complete graph is just going to be 1 plus x to the n minus 1, because we need to have at least 1 vertex in our dominating set. So this is just taking away the empty set. So if we look on 8 vertices here, so the domination polynomial of this graph is written out here, and we can see that it's unimodal because it increases up to x to the 4, and then afterwards, kind of did that backwards, but it doesn't really matter. And it's also log concave. If we were to check each of these, we would see that 28 squared is greater than 56 times 8, and so on. Now, in general, domination polynomials are not log concave. The smallest example happens on 9 vertices, this graph right here. And we can see this is unimodal, having its peak at x to the 5, or its mode at x to the 5. But if we look here at x cubed, the coefficient is 7. If you square that, we get 49, but that's less than 50 times 1. So this is unimodal, but it's not log concave. And there's been an open conjecture since 2009 about domination polynomials, and that just states that domination polynomial of any graph is unimodal. Unimodality and log concavity has been looked at for many other different graph polynomials. All matching polynomials have been shown to be log concave, That was actually proved in two different ways in 1972 and 1996. The independence polynomial of claw-free graphs, so not all graphs, but just claw-free graphs, has also been shown to be log-concave. There's also been multiple different proofs of that. Chromatic polynomials are log-concave, and dependent set polynomials have also been shown to be log-concave. So today we're just going to be looking at domination polynomials. So before we jump into a general sense, we'll talk about paths and cycles. So for domination polynomials, paths and cycles follow a kind of a nice recurrence relation here, which basically says that if you take a path or a cycle on n vertices, such as a string of vertices or just like a circle of vertices with n of them, if we were to take that domination polynomial, that's going to be equal to the domination polynomial of a path of 1 fewer, 2 fewer, and 3 fewer vertices, all added up and multiplied by x. And the same is true for cycles. So here I've written out for a path on n vertices. I know some people use Pn to be the number. Sometimes we don't have, there's not always the same notation, but I use n to denote the number of vertices in a graph. So here I've just written out the domination polynomial of a path of up to 7 vertices. And if we were to kind of check out each of these coefficients, we'd see, okay, this coefficient of x to the 5 is just going to be the coefficient of x to the 4 for the previous 3 all added up. And we see we get 19. So one other thing you'll notice is that each of these are unimodal, and their mode is increasing or staying the same each time. So the mode of a path on 2 vertices happens at x. On a path on 3 vertices happens at x squared. 4 vertices, you can kind of pick or choose to be x squared or x cubed. It doesn't really matter. The way we've defined it is kind of ambiguous. But if we keep going up, the mode kind of increases very slowly as we increase the length of our path. And it turns out that if you have kind of this property for your small graphs, so your small paths and your small cycles, that property is going to hold true for the rest of the paths. We prove this in general just for polynomials. So if you have a sequence of polynomials that satisfy that same recurrence relation, if the first 4 polynomials are unimodal and the mode increases by either 0 or 1 each time, then that entire family is going to be unimodal. And that tells us that paths and cycles are unimodal. There's actually a large family of graphs outside of these two, but just are not very significant, that this will hold true for. And we can use this as a tool to show that those families are unimodal. So in general, what do we know? In general, it was actually shown fairly early that the first half of the coefficients of x will be of x up to x to n over 2 increase no matter what graph we have. This has nothing to do with dominating sets. This is actually only because of the fact that a sub-property that dominating sets have, which is if you take a dominating set and you're to add 1 additional vertex or any amount of additional vertices to it, it's still going to be dominating. And that kind of makes sense because if we have a vertex that's not in our dominating set, it's going to be adjacent to something. And if we added another vertex somewhere else, it's still going to be adjacent to something. So this new set is also going to be dominating. Sometimes people call that closed upward or complement of a simplicial complex, something like that. Basically, that property is very important, and that's why we get this kind of increasing to n over 2. Now, on the other half, if we look downwards from our highest coefficients, x to the n minus 1, down to x to the n minus our minimum degree of our graph, well, we're actually going to get those binomial coefficients again. And basically, this stems from the fact that you have to remove a certain number of vertices before you can have a subset of vertices that doesn't dominate the graph. Because if every vertex needs to be adjacent to something, we need to at least remove every vertex in that it's adjacent to before that vertex can't be dominated. So right away, we get this kind of somewhat trivial resulting unimodality, which says if our minimum degree is at least half the number of vertices, then the domination polynomial of that graph is going to be unimodal. And what we're going to do is we're basically going to extend this to go not be at n over 2, but we're going to extend it down further to be 2 log 2n. So the way we did this is we said, we looked at the proportion of subsets of vertices which are dominating. So for each I between 0 and n, we looked at the number of dominating sets of size I divided by all the possible subsets of size I. And because of this closed upward property and the other property where every subset is dominating once you get past the minimum degree or n minus the minimum degree, then these proportions are actually going to be increasing, or at least not decreasing, up until r n minus delta. And they're always going to be between 0 and 1, obviously because we're talking about a proportion. So this also gives us a necessary and sufficient condition on when our coefficients are increasing or decreasing, now based on this proportion. And we can kind of replace this Rn plus 1 with the maximum value 1 and get this nice little condition that if once that proportion gets close enough to 1, then our coefficients are going to decrease afterwards. And basically all we did was we just kind of took some bounds and said, okay, based on our minimum degree, what proportion of dominating sets could possibly be non-dominating, which obviously gives us the dominating ones. And we got this bound on the proportion to be 1, that this proportion Ri is at least 1 minus n minus I times n minus I over n, which is going to be less than 1 to the delta. So if we increase the minimum degree big enough, this is going to get closer and closer to 1, which is then going to tell us that our coefficients are going to be decreasing after some point. And because we know it's increasing up to n over 2, if we can show it's decreasing after n over 2, we get unimodality, and we get the mode is exactly at n over 2. And that's exactly what we showed. So the delta that's required is if our minimum degree is at least 2 log 2n, then our domination polynomial is going to be unimodal, and the mode is going to be at n over 2, or the ceiling of n over 2. And we think about this in a probabilistic sense. Well, if we took a random graph, and you can actually pick kind of any probability, if we have a kind of a fixed probability for every edge, that probability can be anywhere between 0 and 1. Then with probability tending to 1, that random graph is going to be unimodal with the mode at n over 2. So generally, this is not a great lower bound. 2 log 2n is going to obviously not cover. There's going to be a large family of graphs that this is not going to cover, but in terms of all graphs, this will get almost all of them, which is kind of nice. So just to conclude with some future work and some open problems. Obviously, it'd be nice to show that every domination polynomial is unimodal, but in particular, graphs with small minimum degrees like trees. Another question is there always a large sequence of decreasing coefficients? So we know that the coefficients from n minus the minimum degree down to n or up to n are going to be decreasing, but can we always increase that? And we think yes, that is always decreasing from 2n over 3 up to n. And the last question, which I think is kind of interesting because I just taught an intro stats course and it's kind of rolling around in my head, is what does the distribution of dominating sets look like? So we kind of see this unimodality, but in another paper that I did with my supervisor, we actually showed that the same family of graphs, so minimum degree at least 2 log 2n, the mean size of dominating sets is between n over 2 and n plus 1 over 2. So that means that we roughly have the same mean and mode for these orders of dominating sets. And we can actually, I think we're also able to show that the median is roughly at n over 2 for the same family. So it kind of begs the question, what does the distribution look like? And I just plotted a distribution for a path on 136 vertices. I chose a path because the mean is not going to be at node number 2, and the coefficients are not really the binomial coefficients. So for example, the complete graph, that's just going to basically have a binomial distribution. But for a path, it's not obvious. But even when you plot it, you get this bell shape and this kind of normal looking distribution. And the distribution itself isn't that interesting, but maybe we can take this and put some bounds statistically on where the smallest dominating set could be, or other things like that. Thank you.
Yeah, thank you very much. So if we could all thank our speaker, so you can, yeah, clap and use the emoji. Okay, so at this time, I want to call, like, if you have any questions for our speaker, you can unmute yourself and ask them, or if you'd like to type it in the chat, I can ask that verbally for you.
So I have a question. So can you so you had this so you mentioned that there was this result if you have a if the polynomials are given by a certain recurrence, then it ensures unimodality. Can you go back to that slide?
Right here.
Yes. Right. So if so these are so you have so is this a result for a general sequence of polynomials Fn?
Yes.
I'm confused because you have like Pn, which, so what are Pn? Are these?
Sorry, this is a weird way to write it, but Pn is just the property that
Okay.
these polynomials are unimodal with the mode increasing in the sequence. But the actual polynomials in the theorem as the statement is Fn.
So if P4 holds, then Pn holds. So how do you so you only assume that F1, F2, and F3 are unimodal, and then you get and F4 is unimodal, and then you get everything else is unimodal, as well as you know where the mode is. As in so how do you prove this? What technique do you use?
Yeah, so the proof is actually pretty straightforward, but I didn't want to totally go through it here. But basically, the idea is once you know where the modes are generally, you know it's kind of within 2 spots of the previous one, you can break it into a few cases. So you kind of fix one of your modes and you say, okay, the next one's either going to be the same or one greater, and then the same and one greater. Like you get 4 cases. And then kind of outside of those possibilities of where the mode could be, you know that the polynomial is going to be kind of increasing up to here. So we kind of, because all of the previous polynomials are unimodal. So you basically need to just settle 1 or 2 inequalities to get that unimodality. And 3 of the 4 cases are pretty straightforward. And the last case isn't too bad, but you actually got to go 1 further to get another equality. And that's why we have n at least 4 instead of 3, just to solve that 3rd case or 4th case.
Right, thank you.
Are there other questions for our speaker?
I have a question. So you said that there was, in general, this polynomial, like for an arbitrary graph, is not log concave, right?
Mm-hmm.
Are there families that you know it is log concave besides the complete graph?
Yeah. There has been a few. So there's so if actually there's a lot of nice constructions to do this, and there's a lot of interesting things, but probably the simplest family I can explain is you take any graph and you corona it with a K1. So what that means is you take every vertex and you add a new vertex just to that one. So you kind of get this spiky looking thing. And those graphs, no matter what graph you started with, actually all have the same polynomial. and they're all log concave. And something more interesting about that, I'll just tuck this in, is that the independence polynomial of these graphs are conjectured to be log concave, but they don't know. Even though all the domination polynomials are the same, the independence polynomial is, they're not sure.
Cool, thank you.
So I do have a, well, first, we don't have a second talk in this session. So if people want to stay a little bit longer for more questions, I think we're able to do that because the next session doesn't start until 10:45. I did have a question, maybe a more general question, but and you actually just answered one of mine because I was wondering, you said, so there are graphs that are non-isomorphic that have the same polynomial, if that's what I'm understanding from your last comment.
Yes. Yeah.
And I was more curious, like I don't know much about these domination numbers, but are there any, like, what type of properties do they have? I guess that's kind of a vague question. Or maybe like, do they have a relationship to like any other invariants associated to a graph, like chromatic number, or I mean, you stated the chromatic polynomial has this property of log concavity that not all.
So are you asking about domination or log concavity, or just?
Yeah, just the domination numbers themselves, like.
So there's a few bounds on each of these things. Probably the nicest relationship is if you took any independent set and you took the complement of it. So let's say your independent set is these vertices, you take all the other vertices. What you end up with is a dominating set.
Okay.
So that kind of gives you an interesting bound. You can bound the independence number kind of on both, or the domination number on both sides using this, because I think you can get like n minus the independence number, and the independence number itself actually also connects to the domination polynomial. So there's this kind of sequence of in like the largest minimal independence, the largest minimal independent set, and the smallest minimal independent set, and the same thing with the dominating sets, our minimal dominating sets. You get this sequence of inequalities between those. So that's probably, between those is the best relationship.
Okay. Yeah, great. Thank you. Are there other questions?
So can I ask just a random question? So when you're proving that, I forget where it was, but like you were trying to show that maybe in the next slide. Yeah, in here, why did you, like on the previous slide, why did you decide to look at the ratio, like the proportion, like to prove this? It just seemed like it was coming out of nowhere to me, at least.
Yeah. So basically, I was thinking about that because I did this work a few months ago, and I was like, if we could do it with the ratio, why couldn't we just do it with DI in the first place? And basically, these properties are why. But mainly this one, which is the big one, which basically says once we get that ratio big enough, then we don't have, we know how they're going to behave afterwards. And you can't really do that with just the number of dominating sets itself, because kind of the differences between these binomial coefficients helps you kind of get that. Basically, the difference between those binomial coefficients and how close we are to the top, they kind of work together to help you show that. There's probably a way to do it without the proportion, but this is just the way that I thought about it.
Okay. Well, why don't we thank our speaker again? Yeah. Thank you, Iain.